Welcome to the pre-recording of lecture 12, which is the second part of the sixth session of the 8-week summer course. So we are starting the third week. This is the second half. In the first half, we introduced loops, and we will continue this exploration of loops with the break statement in Python, explaining how it's often good if the condition comes not at the beginning of the loop, but somewhere, anywhere where you want it. So the break statement is extremely flexible. Computer science studies algorithms, and an algorithm is an ordered set of unambiguous steps that are executable and that lead to a terminating process. So there are many examples of algorithms. And one of the top 10 algorithms of the 20th century, of the last century, if you like, are Monte Carlo methods. So this is the bottom line of the slide. I will use simulation as one of the examples that we are using to introduce loops, but at the same time, uh, it is one of the applications of computers to work out different um, different models, mathematical models, to simulate uncertainties and kind of compute probabilities of events. One can also see it as a way to evaluate very high dimensional numeric integrals numerically. Evaluate is probably a bad word. I should say estimate. So simulation is important, an important application. So, and we will use this as an illustration, as a motivation for our loops. So how does it run? Well, the second bullet point essentially states the algorithm. So what we are doing is that repeatedly we are generating numbers according to some probability distribution. We do a test on these numbers. So if we flip a coin, we generate a random number between 0 and 1, and we check the number of times that a number in the first half versus the second half occurs. So can we use our uniform random number generator as a way to simulate flipping the coins? So if you do this for 10, and actually earlier in the earlier lecture we've seen that dictionaries have tools built in, dictionaries and lists. They have tools to actually build a frequency table without any loops or with list comprehensions. But here we will do this with explicit loops. Um, so what I was about to say is that if you're doing this for 10 numbers, then you may have very skewed results. But if you do this for larger and larger numbers, so take millions of numbers, billions of numbers, then you should see that the expected value, what you compute, corresponds to mathematically what you would expect. Okay, so flowcharts are very useful for loops because what does a loop have? What are the most important ingredients in a loop? There is the initialization. So here we will initialize a sum s and a counter I. So I is an index. Then we have the two tests. We are going to do no more than n trials. Think about an experiment. So we are simulating experiments, no more than n experiments. And we are going to count the number of times that our experiments leads to a success or not. So this is a very general template for a simulation. We have a loop, so flowcharts are quite natural with the arrows to give the flow, and we can return to any point earlier on in the sequence of instructions. So where we have the initialization, the statement all the way at the top, and everything that comes below it, except the print s, that's the end statement where we print only once the result, the sum of our successes. Everything outside the print and the initialization is called the body of the loop. Um, so we have a stop condition, and then we also have a test inside the loop. So we can have if statements inside a loop. So we introduced if statements before and then loop statements after, but we can mix them. So we can put an if statements inside a loop. So the test on success is such a statement inside a loop, a test inside a loop. Okay, so here is our running example. So this course follows, or actually has as prerequisite, calculus. You may have encountered integrals already in calculus. So in a way, this is not a good example if you know calculus, but the same idea applies to very high dimensional integrals. In multivariate calculus, you will go to two-dimensional integrals, three-dimensional integrals. But what if you have 10-dimensional integrals? What if you have 10 parameters? Then evaluating a 10-dimensional integral according to the rules of calculus might no longer be possible, and even numerically may not be even desirable. So what you then can do is you can estimate. So the algorithm that we are introducing here seems extremely naive. So we can generate random numbers uniformly distributed inside an interval. Here the interval is -1 plus 1. And we generate two of them. So geometrically, you represent this as throwing a dart inside a square box. So the first coordinate, the x, is between -1 and +1. The second coordinate, y, is also between -1 and +1. So you can imagine, and actually one of the exercises is that you build a turtle application that is actually going to have your turtle running around the canvas at randomly, and that is going to mark a dot for each random number. So that's a very nice visualization of throwing darts inside a square. So ones that you throw outside, they are completely discarded. So we will always throw inside the square. And then we count as a success if the random point falls within the unit disk. And there is a very quick test on this. X squared plus y squared is 1 or less. So that is the criterion for success. So we are evaluating an integral, but we're doing this with a simulation. So here you see the same flow chart as we started with, but now fine-tuned for the particular application of estimating pi. We initialize again at the same way. What we actually are printing and what we are computing will actually be, I'm sorry, so this is still a problem here. So the 4 should not have been, oops, I'm doing something now completely wrong. I should fix this. So we are printing the sum here, and actually also here we should print the sum divided by n. The 4 might not be needed. So there is the test on success. There is a stops test that has not changed. Here we have the counting of the success, the if inside the loop. Okay, I will, in the second half of the lecture, go into a Jupyter notebook and then into the scripts. Let's look at some motivations. So here we have the binary expansion, so which we introduced already very early on in our first session as one of the key algorithms. Then we did this essentially by hand or used the Jupyter notebook as a calculator. Now we know enough to actually compute this. And in the previous session, where we looked at using lists as stacks, we have seen how we can store all the bits in a stack so that when we print them, they appear in the right order. Um, so I'm also using this to illustrate again the notion of a state table. We are going to compute in each step of the loop one row in the table. So each time we replace the number n by its quotient. So the quotient is shown in the second column. So we divide repeatedly by 2. And the remainders will be the bits in the binary expansion. The problem is that the bits come up in the wrong order. But we have already solved this problem with the stack. The other point that I want to make is that the stop condition is that when the number n becomes 0 or not. So what we actually are doing is that we are running, we are actually computing each time the quotient, and as long as that quotient is different from 0, we actually continue. So we can actually better often use a repeat until than a while loop. Okay, that's one. So here you see the input. So we will actually always print at least if the number is 0, then we will have to print 0. So the division might not be so obvious, but so you could say if the number, but here you see the flow chart. We have a loop, so but the test comes after we compute the quotient. So as long as the number is not 0, we continue. So if the test is false, we go again computing the quotient and the remainder after division by 2. So, and here we are printing the bits in the binary expansion one after the other. This pattern of leaving a loop or doing first a computation and then testing occurs extremely frequently. And in some sense, it's not strictly necessary. You could do this with a while, but you have duplication of statements, and that can lead to error, can lead to discrepancy. So it could be that you change something inside the loop, but you forget to change it in the initialization. So, or you are inconsistent. So in order to break out of a loop, we have the break statement. So the condition is actually then done at the very end here. Now the body of the loop could be splitted, so you could be intermediately, you could have a test anywhere inside the loop. So this is also, and I'm explaining this here for a while loop where it's typical, but you could essentially also break out of a for loop. Often, when you run a method, you have a fixed upper bound on the amount of work that you're willing to do. But you may leave earlier if, say, your algorithm has already converged. So that's also a typical pattern that we often use in numerical analysis, where the while is replaced by a for loop, with then the maximum number of times we execute the loop. Here we do the while true. So the while true will always succeed. So if there is no break in this loop, then it will go on forever. Again, there are techniques. If you run it at the terminal, Control C, hold the control, and then also at the same time press the C. That's often a very good thing to do. Then you don't have to reboot your computer, for example, or turn off the power cords to make your computer stop. The break is here shown in this Backus-Naur form, so whatever is in between the less than, larger than, are some statements that, or a condition that needs to be filled in. We will not do this here in this lecture, but often loops are also occurring within loops, or loops contain loops, so we call them double loops. If you work with tables, and we have already introduced a mileage table, if you work with two-dimensional tables, and a list is one-dimensional, but you can have a list of lists. So then actually it's typically to work with a double loop. The break will leave only the loop where it, the break statement where it occurs. Okay, so I end with a suggestion for a game. So here is a very plain, simple game. We will see how to generate random numbers. So you can have your computer generate a random number and then don't show it to the user. And then in the loop, you make a guess. You prompt the user for a guess. If that guess equals the secret, then you can congratulate the user. The loop ends. Otherwise, you ask the user to continue. So this is the prototypal construction of what we call a repeat until. We have a loop, but the condition appears at the end of the body. So there is a body and there is actually a condition that happens after we have already prompted the user. There are tricks. I mean, so you can, for example, you can do this with a while, but initiate. So if your secret is a positive number, then you can initialize your guess with -1. And then the test while G is not the secret, while your guess is not the secret, will actually initially, indeed go through. So the break is often by convenience, but often when people design algorithms, they have patterns such as these in mind, and a break makes that much more convenient to express in a program what logically was intended. Very convenient. All right, so the purpose of the lectures is always that we can do the exercises. So in some sense, this lecture is also about if statements inside loops. We've seen the nested if, the if else elif, or the if elif else. So we had the code to assign the letter grade. So assume that you have, say, numbers between 100 with 0 and 100 randomly generated. So given a list, so you can actually type them in, but it's much better to generate a list of numbers. I say here numbers between 0 and 100. So it's okay if you do this with 10, but you can also generate 100 numbers. Um, if you are assigning letter grades, then the list of numbers is transformed into a list of letter grades. And in some sense, this is also a test, and if you use a random number generator, is a test on how well the uniform distribution of numbers, how well this. So in some sense, if you have 100 numbers, you would expect only 10% of the numbers to be assigned to letter A. So the exercise 1 is actually a precursor for writing the program. If you are an experienced programmer, you won't need a flowchart, but it's now also a good opportunity to go back to the if else example that we have seen. So, and if you have that flowcharts are actually quite good in the sense that you can very easily make a loop by just drawing one extra arrow. Um, we have already done exercise 3, the middle exercise. So there is the count on count is something you can count the number of occurrences in a list. So count is an intrinsic operation on lists. And to be very honest, when I learned Python, I didn't know about that method. And actually, um, any programmer should be able to make a frequency table without these tools. So it's only because Python is high productivity that actually you will count this by an if inside a for loop. So that's important. 4 is more ambitious. Or if you actually are geometric and visually oriented. So we will actually see that generating 1 million numbers goes extremely fast for current computers. Perhaps a bit too fast sometimes. The nice thing about having programs that run slow is that you're forced to think what is actually really happening. So the exercise 4 is intended to think about this a little bit. So you will also see your turtle going around canvas. Make sure that you scale this up. A canvas is typically several hundred pixels. So the difficulty of this fourth exercise is that you have to map -1 to 1 to, say, the bounds of the canvas. It's also okay to take the upper quarter of the circle. So if you can do this for pi over 4, you have pi. So you can generate random numbers between 0 and 1, or actually between 0 and the size of your canvas. So there is a method so to actually, or you can experimentally determine how far you can go in the x and the y direction. I will give a program to guess a number. And if you don't give any feedback, then that number should not be large. So the secret that I will generate will be a number, one single digit number. no larger than 9. Because if there is no feedback, and say you are generating numbers between 0 and 1000, it could cost the user hundreds of guesses to do it. So in some sense, exercise 5 allows you to experience the efficiency of binary search. If the computer not simply tells you that the guess is right or wrong, but also tells you that your guess was too small or too large, you can take advantage of that feedback. Again, this is an exercise of having an if inside a loop statement. And that's actually the whole point of this entire lecture. The if is one basic control structure. The loop is another main control structure. Um, and they have to work together. So you have to be able to use them in combination to write good programs. So learning about how to combine them is important. Okay, I have a notebook prepared, and in some sense, this is already a little bit of a hybrid. The notebook is good to illustrate things. So you see here a random number sitting. When I execute this, so I will do this multiple times now. You see I'm doing this until I have a negative number. Okay, so there we are. You see that the uniform number generator is imported as the small letter u, and that is for my convenience. You see, when I'm going to generate random coordinates, I'm going to call that function twice. And it's good if it has a very small, um, so it's actually programmer-wise not really that the smartest way to do, because I cannot, if I would want to use the variable u, that wouldn't be possible. But here for this small program, so you can see if I run this statement, it goes immediately through 1 million numbers, and it already gives me 3.14. Um, what I said was that the break, so this, I'm sorry, so this is an example where an if test occurs inside a for loop. Um, as far as accuracy goes, we know what is pi. We could actually also uh, test on the accuracy of the estimate. We can do, say, I'm actually not entirely sure how many numbers we would really, how many experiments we would really need to do to have, say, 5 decimal places of accuracy. You could stop as soon as the error is less than 10 to the power minus 5. That could be an application. Okay, so this is an illustration of simulation, how the flowcharts of the slides translate into actual code. There are also scripts that I will show. What you will do to get to a script, you will prompt the user for this NBR here. So the NBR is 10 million, is a fixed constant. In a program, you will have an input statement, and you will also have an output statement. And then also, because this is pi, you can also print out the error. Okay, I only have 2 sections in there, but what I was doing, I was taking the code of the previous notebook. So in the actual lecture, I may go back and forth the Jupyter notebooks in the same session. So the code that is in this execution cell, and in a way, this is not entirely recommended for beginning programmers. Immediately start with an entire program essentially inside one code cell. It's extremely good if you develop that you have only one statement, or perhaps two or so, that you're very frugal with what you put into a code block. But this is a program that was copied from the previous lecture, so let me click on it and execute it. So what the program does, it prints the state table. So there are three variables. So A and B are in some sense the inputs. So in a way you might be uncomfortable that the A and the B are changing. And I also had this uncomfortable feeling. That's why I'm actually making a string that has the A and the B sitting in there. So with the format strings, we are going to make the decimal representation of the given numbers A and B and put them inside a string that we then display at the end. So GCD AB is actually going to display whatever the A and the B are. So the A and the B are inputs, but there also are variables inside the loop. They're changing along with the remainder. So in the state table, we are printing the evolution of these three variables. So each time when we do a computation, so we compute a remainder, we are going to we compute a remainder, and we also shuffle A and B. So we actually are printing out the current values in each step. So the state table also has a row 0. In some sense, it's good now that Python starts from 0. So for every row, we have the current values of the variables that change inside the loop. But we also have to print out before the loop starts what the initial values are. So in a way, this also then indicates the the correctness of the initialization. So we have the stop test. As long as the remainder is non-zero, we continue the loop. Again, very important, Python is block-oriented, but it doesn't have any specific keywords to mark the beginning and the end of a block. All the statements that are preceded by the same number of spaces belong to the same block. All right, so now the main point of this, so this is a perfectly good, correct program. If you like, you could have, so this can always improve, you could essentially also print the step number. That could be an exercise. So I was saying row 0. So row 0 is the first row after the initialization, before the loop starts. You could actually print out the row numbers and see how many steps this algorithm really needs. All right, but there is another important improvement, and that is the motivation for the break statement. You see that we are computing the remainder before the while because we have to test on that remainder. So you could cheat a little bit and assign the remainder to -1. Then the test will also yield true because -1 is not 0. But that's kind of a trick. And if you like tricks that work, it works, it will work. But it's actually not really nice that and actually with the state table, we have two statements here. So two statements that are repeated. Okay, here is how we can do this better so this program, so you can see if I run this, it prints exactly the same. So when it prints the same, when the output is the same, you could say it's a completely equivalent program. But you can see that it is shorter. So essentially all the programs in this course are short. So it's actually still so short that it fits on one screen here. So I think you can see, well, you don't see the all the way the top statement of the first of the other code cell, but I think you get the point. The loop, the body of the loop is a little bit longer. I admit that. So you have the break, and it's good practice to also put the break on a second line. So it's not entirely wrong to put if r equals 0 colon break without a new line, but it's better practice. A break is actually a break also in the loop. So to emphasize this, and it's has to be, so the four spaces are again very important. We actually, so you could have a break anywhere if you, but then you would break as soon as you execute the body of the loop. So it is a statement that is only executed if the test, if the remainder equals 0, if that evaluates to true. Notice that the break actually really breaks the loop in two halves. So we have the computation of the remainder, and then we have the reassignments of A and B. So the value of B gets assigned to A, the value of the remainder gets assigned to B. So this simultaneous tuple assignment, actually you should only do it if you uh, if the remainder is actually not 0. Because important here actually that the greatest common divisor is B. So if you would still do it, you could say, well, what's the point? It's an extra statement. But when you then put out B, when you then print B, you would actually print 0 because the loop stopped when the remainder equals 0. So I'm doing a lot of talking here. Computer programs are currently executed very, very quickly, and you have the impression that everything should be over snap. But it's very good if you look at code that you try statement per statement, that you try to understand why the statements are organized in the way they are. So why the break statement that is put here is actually here smack in the middle. Okay, so that's the main point that I want to illustrate with the Jupyter notebook. What actually one point in the, and that's actually the last statement here, the last exercise. It's actually the guessing of the secret that I want to demonstrate now. Jupyter notebooks are not very good for input statements. They can be used, but running a notebook with input statements is rather awkward and unnatural. Instead, I'm going to show how the program runs. So I call the program secret guess, and it will be posted on the website. So I will make a guess. Let me make 5, 4, 3, and I found it. Great. I'm lucky. But actually, the only strategy that you have when you run this is essentially by enumerating all possibilities. So I'm lucky that my random numbers are rather small. If in the other if I would have started with 9 and then subtracted, I would have needed a lot more guesses. So this is the point here. So let me go to the code. So this is a .py file. So you edit this when you go to launcher. You pick the Python editor to the editor to generate to make .py files. It's good practice to start with one comment line, which is mainly the lecture where we see this. So in a way, if you have downloaded all the .py files in one single folder, you can see where the what the motivation, where the explanation of which lecture it comes. There is a documentation string, not strictly necessary. All this is ignored by the Python interpreter, but it's important that we declare for ourselves, for our future selves, what the program does. So what does the program? So it imports the function rand_in from the module random. And it generates a secret number. Initially, when I tried this, I did from 0 to 99, but then I got very frustrated because it took a very long time for finding that number. So if you so I would encourage you to do this too. Replace the 9 by 99. But if the computer does not give you any feedback other than wrong, it will take a very long time. So solving the exercise is comparing. So you will have an else after the if. So you will still have if the guess equals, this matches the secret, then you will break out of it. Else, and else you will actually, so the wrong statement will be replaced. So else if the secret is less, so this is an elif statement, or an else if you do not want to use the elif, but the elif will test if the guess is less than the secret. And then you will actually say that the guess was too low, please try again. And then in the else, in the default, so it's not equal, it's not too low, then it is too large. Then you will say too large, please try again. So statement 15 needs to be changed, and that will allow you to play the game with a binary search. And then actually you can afford to have very, very large numbers, because it will depend then on the size of the number. The size in the number of bits. So in every trial you can narrow down, you actually gain 1 bit in the secret. Here with this search, the only algorithm that you can run is actually a for loop over all the possible numbers, that all the possible secrets. And this could be also a good application for a loop. You could place a loop around this. So instead of while true, you could do for a number in the range of 9 here, and replace for guess inside the list of in the range 0 to 9, and then you will do the test each time. Okay, so that's one of the scripts I wanted to show. The other script is the Monte Carlo simulation. Um, so in the Jupyter notebook, the number was fixed to 10 to the power 6. But you may want to run this for larger numbers. So you may want to run this for 100 million, why not? And see what your estimate will be. So what is new? So there is the input statement, the conversion, the casting to an integer, and then also the formatted printing of the estimate of pi. So that is the other script. I have no script for the greatest common divisor, so this could be a good exercise. Or perhaps I do have time. So let me illustrate how you can quickly now build from the Jupyter notebook we have. So I did Control C, I copied. So I'm going to my Python file, I will paste. So this is the execution of the greatest common divisor. So the user is prompted for 2 numbers. and the greatest common divisor is computed along with the printing of the state table. So, and this is untitled, which should make everybody nervous. So here you see the nice thing about having one extra line. So I will go call this GCD state. So let me rename the Python file. So this will be renamed. Oops, did I rename this? So let me illustrate this, how this is going. So I go to my menu, file, rename Python file, remove the untitled, and then GCD state. Okay, oops. There we go. I could run this, but perhaps I should run this. It's always good to, so when you copy something from a code cell in a Jupyter notebook, it could well be, you see, it's actually not good because it actually really doesn't do anything. So I did something wrong then. So what happened is that, what did happen? Um, so when I ran this, nothing happened. So let me save this. So this could be another possibility. Save, I renamed it, but it wasn't really saved. There we go. So we've seen the buffering of files. So our programs are so short is that the editor didn't really bother to saving it. So I needed explicitly to save it. All right, now I know that the copy and paste worked. It's not such a useful program yet because I have this here. So I have to prompt for a input, give a, and then you see automatically it wants to make an indentation, which I find annoying. Give a and give b, and perhaps let's put a space here. So that makes the program more interactive. I think it's Control S by saving. So let me execute this. And I indeed forgot a comma. So running things immediately after you make a modification is the recommended practice. And now I don't have any much inspiration for numbers. And actually, it is good practice to also take the values for which it worked earlier. Okay, let me double to a case 120, 102, and I have the greatest common divisor 6. I have 1 minute left to be more pedantic about this. So in the state table, I will actually print out the initialization. So I have Control C. I have to print the state. And now the R is 0. Now also I have a step counter. So I will be the step counter. That will be the row in the table. So I start at 0, but now I have an I, perhaps the I here, I can initialize it to 0. And now I can use I. And each time I will actually, every time when I do something, I will count this as another step. So I will increment I by 1. If I didn't make any type error, so do Control C and save. And in the last 10 seconds, I can show what was supposed to happen. Here you see now the complete state table with the initials, so initial values, and then for every step, what is happening with the computations. Okay, I'm running now. I'm doing running over time, and I'm sorry about this. But I hope that this lecture was interesting. It is an important concept, having conditional statements inside a loop. That makes for that's a very important notion to think about when you write useful programs.